So what is really exciting about the project that I have now with the Coral Defense Project funded by the Bailey Wildlife Foundation is that we are able to try to come up with new technologies that to work against climate change. And this is a type of project that you just can't do with federal or state funding. It's too risky, but the Bailey Wildlife Foundation believe in taking risks that may pay off in a big way for wildlife. And so that's why we're so lucky to be supported by them. Well, we are so lucky to have one of the board members here in Easton, Bill Bailey, and he had been on a tour at Horn Point, knew about our work. And this was 15 or 20 years, no, 15 years ago. I found out about the Bailey Wildlife Foundation. I met Bill Bailey and submitted a proposal about that microscope right over there. There's a special automated stage that allows us to take a picture of an oyster larvae, move the slide, take another picture, and do something revolutionary. That was my first of several grants, smaller grants from the Bailey Wildlife Foundation, establishing a relationship with them. And then something happened in their financial portfolio, and they did come back and say, are you interested in submitting a proposal for something larger? And I said, of course, yes. And we'd really like to pursue trying to capture carbon dioxide into calcium carbonate. We want to try to emulate the processes that happen in nature for making calcium carbonate in our lab and try to harness that technology to pull carbon dioxide out of the sky and bind it into something that coral reefs can grow on, coral can grow on, to try to make artificial coral reefs. The big strategy is hopefully one of the technologies we come up with could scale up enough to really help reverse global climate change. Actually, we have 3 teams working on this. We have 2 teams in Baltimore at the Institute of Marine and Environmental Technology, our sister lab in IMET. And then 1 team here. All of our teams have been able to create something that's like calcium carbonate. I have some neat stuff going on here, so I'm getting a little bit of calcium carbonate, which is exciting because we're pulling it out of the air and making it into tiny little crystals, little rocks. So whether or not that's going to scale up and be meaningful, that's the numbers, that's the chemistry that I'm doing, trying to find out if it has any hope. But so now that we know we can control the process, now we can optimize it. It's a 5-year project, and at the end of this year, we're supposed to have a plan to build everything into a shipping container. Our goal is to have a solar-powered shipping container that can make one kind of large, 3-foot-high synthetic coral structure in about a month. So, of course, we want to do things faster, but we're setting a reasonable goal. If we could actually build a shipping container that makes a carbon negative coral habitat dome in 1 month, then we would be very excited about that. We have our 3 teams kind of competing. We're like I would call it sibling competition. We all want each other to do well, and we also want to do well ourselves. And we have a decision set for this late spring to find out whose technology is going to go in the shipping container. I really feel like this grant is a privilege to be able to address a great concern of mine, something that is so looming for my son's future. You know, this I try not to think about the terrible things that could happen because of climate change and just think about, okay, I have the privilege to work on a solution, and I hope we will contribute to the many people out there who are also working on a solution. I call it the Hail Mary. Yeah, right. You know, a colleague of mine up at MIT called it the Hail Mary, that someone's going to come up with a technology that really will be a game changer and help us move carbon dioxide out of the atmosphere, which we must do. Yeah. You know, it's not enough to just stop emission. We really do need to pull CO2 out. There are a lot of people who know how to scale up, and we have people on our team who've actually worked in industry in in the cement industry, the pulp and paper, shipping container, just all types of industry who know a lot about scaling up. And we have created a spreadsheet where we list all the numbers that we need so we can compare our technologies well. I hope there is a new phase. That means I hope there is some kind of water in our technology, or like after we run the numbers, we find that there is hope for one of these technologies or all three of these technologies that we have created. And in that case, we will definitely go forward. If we run the numbers and just don't see much from it, then it is an interesting thing that we found, but it's not something that we'll put a lot of our life's work into. So, but if it works out, yeah, I'm gonna take it as high as I can go. This is just proof of concept.
I see.
And we're using one algae species here, and there could be many more. There's all these different things you could do with the algae. There's so many different ways to optimize the process. I feel like we're only just starting to really find out what we can do. It's almost like a whole, most of the algae has been raised at a pH. So I'm going to explain pH, if that's okay. So something that's acidic like lemon juice is low pH. Something that's basic like milk is high pH, and you can taste the difference. There's one's really sharp and one's kind of smoother. Well, most of the algae grown at 7 or 9 pH, and our algae go to 11. And so this is a whole new world of what can you do with the fluid coming off of our algae cultures. And if we can find, say, an algae that is in biofuel and also makes this high pH, then there's an extra carbon credit for the biofuel industry by precipitating calcium carbonate, binding some carbon dioxide from the sky. So, those are the types of ancillary technologies or applications that we're hoping come out of this. So one of my colleagues in this project, Scott Hunsiker, said we're not looking for a silver bullet, we're looking for silver buckshot, a whole bunch of little things that are going to add up to really pulling the CO2 out of the sky. And these special algae, they actually change the fluid and raise the pH of the fluid. And when you get the pH high enough, if you just add some seawater, you get calcium carbonate crystals form. And so that is the really exciting thing, is so the algae are the assist. They're the ones who are pulling in the carbon dioxide and transforming the fluid that they're surrounded in into something that will precipitate calcium carbonate. So how fortunate I am that the Bailey Wildlife Foundation folks have similar ethics, similar vision, and the means to try to make change. It's really, I feel very fortunate.